This demo shows the working of our policy-driven solution for distributed collaborative computations. The MARSAL solution is based on the specification of policies supporting 3 different levels of visibility: no visibility, plain text visibility, and encrypted visibility. Our approach then finds an allocation of the different operation of a computation to subjects to minimize a parameter of interest, such as the overall economic cost. This solution has been described in deliverables D5.2 and D5.4. The reference scenario considers storage, computing, and network resources offered by data centers in the MARSAL architecture. Data owners have authority over the data managed by their nodes and can regulate how their data can be accessed or shared with others. This slide shows an example of the working of our solution. This table shows the authorizations defined by each data owner. More precisely, we assume that there are 2 relations, one at owner P and another one at owner M. Here, there is an example of query that selects for each video class the average duration of recordings, considering only duration greater than 60 seconds. This slide first shows the query triplen, then the query triplen enriched with the relation profiles that represent the information content of each base relation and derived relation. That is the relation resulting from the computation of an operation. Then we reported the set of candidates for each operation, and finally the assignees, selected according to specific criteria, in our case, the economic cost. Our application works in 2 steps. The first step computes for each node of the query plan the set of candidates that are authorized to execute the node operation. The solution is implemented in Python and takes as input some JSON files describing the schema of the involved relations, the query plan, and a set of subjects, that is, owners of the relations, external providers, and the subject submitting the query, along with their authorizations. The application returns for each node its candidate, as well as the relation profile of the node, assuming that all attributes are encrypted, but the one that must be in plain text for the execution of the operation. The second step computes, based on the data produced by the first step, a minimum cost assignment for the input query triplen. The problem is represented as a binary programming problem that minimizes in our setting, an objective function representing the economic cost entailed by the allocation subject to a set of constraints, modeling our problem. The economic cost includes the cost of operation execution, the cost of transferring data among subjects, and the cost of the encryption-decryption operations needed to make the assignment authorized and the operation executable. The problem is solved leveraging Lingo. We now show how our application works in the CTTC testbed. First, we open a connection with CTTC via VPN Connect. We then connect to the machine. We can now run our application. There are different configuration files corresponding to different queries, and in this case, we select the configuration number 4, that is based on the same 2 relations that we saw in the previous slides. For each node of the query, our application computes first the set of candidates. As you can see here, for example, this is the set of candidates for node number 7. And then the assignee using Lingo for optimization. We can also graphically see the input query and the output. This is the initial query, and this is the output. As you can see, each node is now associated with its relation profile, the set of candidates, and the selected assignee. The assignees here are represented in blue. Finally, we can stop our application.